Hello, my name is Stanley and I'll be presenting execution-guided overapproximation, EGO, for improving scalability of neural network verification. I'll be joining Stony Brook University this fall as an assistant professor. What is meant by neural network verification? So, it's the title, it's the focus of this workshop, but I'm particularly interested in the open-loop neural network verification problem. So this is looking at a single execution of a neural network, which is computing some function. If you're given some constraints on the input set, for example, interval bounds on all of the inputs, what are the possible outputs? And in particular, it's when there is a specification present. So you want to prove some property about the output. For example, some output is possible or is not possible. Right? And so the work I'm building on is the star set analysis method. So the star set analysis method is sort of a data structure that can efficiently encode arbitrary linear or affine transformations as well as intersections. What this means is that if you have a piecewise linear neural network, if you have only RELU activation functions, fully connected layers, convolutional layers, average max pooling layers, and a handful of other layers, you can actually do exact analysis in this case. And so I'm building upon this sort of method, looking at different optimizations to speed it up. In particular, I'm looking at RELU activation functions, which compute the maximum of the input and zero. So shown on the bottom is x, which is the input, and y, which is the output. And so in general, a RELU is a nonlinear function. You have two linear regions and sort of non-convex. But that's not always the case if you have input constraints. For example, say you had constraints on the inputs based on the constraints, the input was strictly positive. Then actually a RELU would be a linear function. It would be an identity function, which is sort of easy to work with. Alternatively, if you could prove, based on the constraints you had that the input is strictly negative, that's also a linear function. This is a projection to zero, so you can also sort of do this efficiently. And with star sets, what you can do is you can handle the sort of the interesting case. So the interesting case is if the input to a particular neuron is both positive or negative. And so with star sets, since you can exactly compute intersections, you could split the set into two parts and then proceed sort of recursively with, in the analysis with two parts. This is a sort of an exact analysis method, and we'll sort of look at that a little bit later in the talk. The talk really is about looking at not just splitting the set, but sometimes doing overapproximations of the set. So a very useful overapproximation is called a zonotope overapproximation, and so this is one example of a zonotope overapproximation. There's actually several zonotope overapproximations you can do of a RELU activation function. This is, I think, the minimum area one, but that doesn't necessarily mean it's always the best. So what you see with the zonotope is that the area inside the zonotope captures everything that's inside the RELU. So if you assume there's some lower and upper bound that you've computed ahead of time, you can use the zonotope to overapproximate the output. And it's there's points that are not possible, but if you can use this to prove safety, it's useful for speeding up the analysis. Right? Zonotopes are very useful because you can optimize over zonotopes without using just a simple loop. So you don't need linear programming or anything complicated. With star sets, you can do a little bit more accurately. So if you see this paper, it has the details. But basically, you can get this triangle overapproximation, which is the best convex overapproximation in this 2D space of input-output of a single neuron. And you can do this efficiently, right? So you can represent this with star sets, and then you can optimize over star sets using linear programming. So it's slower than zonotopes, but it's more accurate, right? So star set verification with partial overapproximation, the way it works is that you assume some ordering of the neurons. And so this is, again, some odd thing we can explore later is, don't assume ordering of neurons or have dynamic orderings. But for now, for simple explanation, just assume you sort all your neurons. You have only fully connected layers and RELU activation functions. And you can sort them, for example, by the layer number and then the row number in the weights matrix, let's say. So the first row in the weights matrix corresponds to a particular neuron, and the layer 0, that's sort of the first neuron that you look at. And if you do it this way and you analyze sort of the inputs to that neuron, you can check if they're strictly positive, strictly negative, or if you need to split. And then after you analyze the first neuron, you can look at the second neuron in the ordering. And so in this sense, the verification problem becomes a tree search. And then at each inner node of the tree, you have a choice where you can either try to do over-approximative analysis, where you take an over-approximation using the triangle over-approximation or the zonotope over-approximation, and continue with over-approximation for the rest of the network, and then try to prove the property. Or you could do a split, and then again, once you split, then you go to the next neuron, and eventually you have the same choice to make too. So that's the general strategy. So we know that verification of these types of networks is NP complete, and it's can be bad in practice. For example, if you just do sort of a splitting strategy, at every RELU you could, in theory, double the number of sets. So a neural network like the ACAS XU benchmark networks have 300 neurons. So in theory, you could have 2 to the 300 sets. But this doesn't always happen in practice. So if you look at some of the ACAS XU networks, depending on if you have very tight constraints on the inputs, you're going to have a lot less splitting that's actually possible in practice. So what we call this exact analysis is the split strategy in this paper. And it turns out even with the split strategy, there's, you can get performance improvements of 10 to 100 times. And so there's this corresponding CAV talk that I gave this year, which hopefully you can look out for that video. And what it does is it looks at a series of optimizations and analyzes them, makes one change to the algorithm, runs all of the ACAS XU neural networks and see how it affects runtime. And so we're able to actually speed up analysis in some examples up to 100 times by doing that, compared with the original star set approach, which is already orders of magnitude faster than the original approaches proposed, when with RELU on certain examples. So this paper sort of builds upon the CAV paper by also looking at partial overapproximation analysis. So rather than just splitting on every single neuron, now we consider the case of do splitting sometimes and do single set overapproximation sometimes with this triangle overapproximation. And notice neither of these two are always best, right? So splitting is nice because you have the most accuracy, but you have this potential exponential splitting, so it can take a long time. Single set overapproximation is nice because there's no splitting, so generally analysis is fast. However, there's overapproximation error, so you might not be able to prove the property that you're interested in proving. So this is a general problem with formal methods, whether you're analyzing software or other sorts of areas, is what's the correct level of overapproximation in order to verify the properties you want. And so a well-known approach for this problem is CEGAR, which is counter-example guided abstraction refinement. And so the CEGAR approach, what they do is they will first try to analyze very coarse overapproximations of the system, check if it proves it's sufficient to prove the property, and if verification fails, you go back and refine, and hopefully you're using your counterexamples that you found to do the refinement. So in our approach, we just use a simple strategy to solve this problem of where to refine, which is we just do it at the first neuron. And so there's advantages to doing that too. So analyzing neural networks, you also have the general problem in formal methods that overapproximation error leads to more overapproximation error. So this happens in neural network analysis, where if I start overapproximating some of the earlier neurons in the network, they'll lead to additional splits later on in the network. So if I were to do refinement later on in the network, those might not actually correspond to real neurons that can split. They might just look like they split because I had error earlier on in the network. So it makes sense to start the splitting earlier on in the analysis because that'll prevent later error. So this sort of simple approach is we just do it at the first neuron, and then analysis really looks like a tree. And so looked at this way, the CEGAR approach generally analyzes sets from more abstract sets that look at the output of the neural network to more concrete sets. So you sort of refine the set over time, starting with the biggest one, and then you get smaller and smaller. And so the potential downside of CEGAR, which isn't often mentioned, but that we notice that occurs when looking at some of the ACAS XE networks, is overapproximation analysis can often take a long time, and it often fails. So to do overapproximation analysis, you need to compute for every neuron that looks like it's splitting, you need to compute the lower and upper bound in order to come up with either the zonotope or triangle overapproximations. And so using the star set method, this is linear programming. And so linear programming, while it's quick and scales high, it's if you have to do it at every neuron, it can potentially still take a long time, and it can sometimes become the bottleneck of the method. Whereas if you split and you didn't have as much overapproximation analysis, maybe you just had to analyze a handful of neurons. So it's like, rather than solving the upper and lower bound for 200 neurons, if I do it for 5 neurons, it's significantly faster to do it for 5 neurons. So overapproximation analysis can take a long time. So the alternative strategy that we propose is what we call EGO, which is execution-guided overapproximation. So the EGO approach to verification first starts out by splitting all the way down until you get to the end of the network, and no more splitting is possible, and then checking the property from this sort of concrete execution. And then you've created a search tree where you have a bunch of branches, and you've sort of gone down in the depth of first search down one of the branches. And then you sort of the search order should be, if you're doing exact analysis, you would back up and do the other branch that's close to the leaves of the tree. But rather than going down that branch, we now start doing over-approximation analysis. So we first get a concrete execution, and then we start building up over-approximation from the concrete execution. So rather than starting with, so the over-approximation starts out with more concrete problems and builds them up to be more and more abstract. And in this way, we avoid the problem of doing analysis where it's very abstract and actually can't prove the property, which can take a long time and doesn't really provide any benefit to us. And so in sort of an abstract view of this exploration order is this figure here. So this is, you could imagine a search tree of looking at various different neurons. So the neuron here in the top is the root of the tree. So this, if you do over-approximation analysis here, it's like looking at the triangle over-approximation on every neuron. If you can imagine instead you do split analysis where you could go down the positive or negative branch of the first neuron, and then the next splitting neuron would be the one shown here. And so the CEGAR order starts at the root of the tree. So first it tries full over-approximation analysis. If that fails, it'll do a split, and then it'll try full over-approximation analysis down one of the branches. If that fails, it'll do a split, and it'll do full over-approximation analysis. So it's really following this 1, 2, 3, 4 order. And let's say the over-approximation analysis succeeds at this node, right? So then it will go down the other branch and try full over-approximation analysis, looking at node 4. Ego, in contrast, would first do a concrete execution of the system. So it'll first go down all these branches without doing any over-approximation analysis until it gets to a point where no more splits are possible. So it's now this A node. And it'll proceed in A, B, C, D order. So say it proves safety of the A node. Then it'll sort of go back and it'll go down the other branch, and now it'll look at the B node and do over-approximation analysis at the B node. Then it'll say the system is still safe. It'll go back and now look at the C node and do full over-approximation analysis at the C node. Then let's say it's still safe. It'll go back and now it'll go to the same node that we got to with CEGAR and try to look at analysis with the D node. So in both of these cases, CEGAR and Ego, 3 nodes are analyzed before getting to this node in the search tree. But the ordering is different. So CEGAR looks at coarse over-approximations, whereas the Ego order looks at more concrete over-approximation, so less abstraction. And so the claim is that sometimes this strategy of looking at more concrete over-approximations can be faster than the CEGAR order. And so we analyze this on many networks. So this is integrated into the NNNM tool, which I'll have a link at the end, and it's also part of the VNN competition. So it's one of many optimizations we looked at, but in particular, just looking at this one specific optimization, we looked at one particular ACAS XU network. We can look at what's the runtime of the approach and compare it with other tools. So this was a particularly hard property in ACAS XU. I think it was the only one supported by ERAN off of the shelf, although they may have added support for more. Using exact analysis as well as some of the optimizations from the CAF paper, this took 62 seconds to solve, which we can see is already very fast, right? And you can see that those optimizations in the CAF paper do matter because NNV in theory is doing the same method as what we're doing. So exact analysis is fast. But then doing partial over-approximation analysis, you can do even faster. So CEGAR in this case took 28 seconds. And then Ego analysis was even faster, taking 15 seconds. And we looked at a bunch of other optimizations. So in the final version, it's a mix of different optimizations. But in this particular case, anyway, Ego analysis was faster. And we can look at concretely what happened when we were exploring the search tree. So let's do that here. That's what. Okay, so here. Zoom in a little bit. So this is showing the search tree actually for this problem. So the search tree is pretty big, so I can't put on one slide. There's like 2,000 nodes in the search tree. But you can look at the start of the search tree. So with over-approximation analysis, CEGAR, the first thing it does is it looks at, it checks if the over-approximation is safe. So what this is showing is that the over-approximation is unsafe at the root of the tree, doing full over-approximation. There's 201 RELUs that split in this case, and analysis took about 3 seconds. So it's fast, but I mean, if you don't want to do this too many times still. But the point of that is that this 3 seconds is completely wasted. There's no, you can't use any information from this other than that you can't analyze at this level. So what CEGAR would do is first it would go down, let's say the positive branch of the first neuron, and then again try over-approximation analysis. And so in this case, now there's 192 RELUs that split, and analysis is a little bit faster. And then if you go down a couple more of the positive branches, you can see that the number of splits decreases and analysis significantly speeds up. This proceeds until you get to this case where over-approximation analysis can now prove the property. And here there's 46 RELUs that split, and analysis is possible in 60 milliseconds, sorry. So this is a lot faster. You can analyze 10, 20, 30 of these, these types of problems in the same time it took you to do this first problem. In the ego approach, the first set that analyzes actually goes down all of the branches until there's no more splitting possible. So now this is actually a concrete system, and you can analyze it very quickly for safety. And then what it does is it slowly backs up the search tree. So it's doing like a depth first search order, and now trying to do overapproximation analysis. In this case, it couldn't do overapproximation because there was no splits that were possible. So that's why this is concrete safe again. Here's the first overapproximation analysis, and you can see that it's actually safe using 9 RELU splits, and it takes about a millisecond. So even though there's actually more problems solved here before you get to sort of a similar case that you had with CEGAR, all of these analysis times are really very quick. So maybe 10 milliseconds right here. And then once you get to an unsafe case, now it takes again 100 milliseconds. So it's and there's 75 splits that occur. So this is kind of a longer time. And again, the ego search order, it'll again once it's unsafe, it'll try to produce another concrete safe trajectory and then sort of back away slowly. So you see these sort of strategy where it sort of produces more and more abstract systems until it can no longer prove the property, such as here, and then it'll go down actually one of the concrete branches and slowly back off there. And so that's sort of why in this particular case we can see that ego analysis can actually be faster in this case. So the sort of summary I want to say is that this is one possible optimization for partial overapproximation analysis, and sort of similar to our CAF paper, which focused on exact analysis. In the future, I think we'll have a paper looking at different optimizations for partial overapproximation and sort of doing a systematic analysis. I mean, the issue is there's so many optimizations you can do, and it's hard to tell which ones make a difference and which ones don't, and which strategies work and which ones don't. So this is one of the more interesting ones, in particular because it's sort of similar, if you think about it, of analyzing more concrete systems to more abstract systems. It's sort of a competitor to CEGAR, and since CEGAR is applied to many different domains, from hybrid systems analysis to software analysis, I think ego analysis could also be applied to these domains. So that's maybe something we can look at in the future. And so again, this is implemented in the NNM repository, and we participated in the VNN competition this year. So please look out for that. Thank you.